Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1995 marked a pivotal moment in the history of physics, witnessing the experimental realization of Bose-Einstein condensation in a dilute gas of rubidium atoms by Eric Cornell and Carl Wieman. This achievement, detailed in their seminal paper, confirmed a prediction made 7 decades prior by Satyendranath Bose and Albert Einstein, opening entirely new avenues of research in quantum mechanics and condensed matter physics. To fully appreciate the significance of this work, one must delve into its theoretical origins, the experimental challenges it overcame, and its subsequent impact on the scientific landscape. The story begins in the mid-1920s, when Bose, an Indian physicist, derived Planck's law for black body radiation. By counting photons as indistinguishable particles, he sent his work to Einstein, who recognized its profound implications and generalized Bose's statistics to massive particles. Einstein predicted that a gas of identical bosons cooled to sufficiently low temperatures would undergo a phase transition, with a macroscopic fraction of the particles occupying the lowest energy state. This phenomenon became known as Bose-Einstein condensation. Despite its theoretical elegance, the experimental verification of Bose-Einstein condensation proved elusive for many years. A primary obstacle was the incredibly low temperatures required. The transition temperature, often termed the critical temperature, is inversely proportional to the particle mass and density to the 2/3 power. For typical densities of ordinary gases, this temperature falls within the microkelvin range, posing immense challenges for cooling and trapping. Early attempts to achieve Bose-Einstein condensation focused on liquid helium, which undergoes a phase transition to a superfluid state at around 2 Kelvin. While superfluidity is related to Bose-Einstein condensation, it is far more complex, involving strong interactions between the helium atoms. This complexity made it challenging to isolate the effects of Bose-Einstein condensation itself. The breakthrough came with the development of laser cooling and trapping techniques in the 1980s. These techniques, pioneered by figures such as Stephen Chu and William Phillips, allowed physicists to cool and confine neutral atoms to unprecedentedly low temperatures. Laser cooling works by shining lasers onto atoms. The light emitted by the lasers slows the atoms down, thereby reducing their temperature. Magneto-optical traps, known as MOTs, further confine atoms by combining magnetic fields and laser beams. Cornell and Wieman, working at the University of Colorado Boulder and the National Institute of Standards and Technology, recognized the potential of these new techniques to achieve Bose-Einstein condensation in a dilute atomic gas. They chose Rubidium-87, an isotope known to be amenable to laser cooling and trapping, for their experiment. Their apparatus consisted of an ultra-high vacuum system to minimize collisions with background gas molecules, a series of lasers for cooling and trapping the rubidium atoms, and a sophisticated magnetic track to further confine and cool the atoms. The critical step in their experiment was evaporative cooling. After trapping the rubidium atoms in a magneto-optical trap and cooling them to around 20 microkelvin, Cornell and Wieman transferred the atoms to a magnetic trap. They then selectively removed the most energetic atoms from the trap, allowing the remaining atoms to re-thermalize at a lower temperature. This process, repeated many times, progressively cooled the atomic cloud to temperatures below 50 nanokelvin. At this ultra-low temperature, Cornell and Wieman observed a dramatic change in the velocity distribution of the rubidium atoms. A distinct peak emerged at 0 velocity, indicating that a significant fraction of the atoms had condensed into the lowest energy state. This peak, a clear signature of Bose-Einstein condensation, provided compelling evidence for the realization of this long-sought-after phenomenon. Their observations were meticulously detailed in their 1995 paper, providing a comprehensive account of their experimental setup, procedures, and results. The paper included detailed images of the velocity distributions, clearly showing the emergence of the condensate. The immediate impact of Cornell and Wieman's work was profound. It provided the first unambiguous experimental confirmation of Bose-Einstein condensation in a weakly interacting gas, opening up new possibilities for studying the macroscopic quantum phenomena. Physicists around the globe quickly replicated their experiment using other atomic species, confirming the universality of Bose-Einstein condensation. Within a few years, condensates of sodium, lithium, and hydrogen were also The creation of Bose-Einstein condensates also led to the development of atom lasers, devices that emit coherent beams of atoms analogous to photons in a laser. Atom lasers promised a range of applications, including precision measurements, atom interferometry, and the creation of novel quantum devices. The field of atom optics, which explores the manipulation of atoms using lasers and magnetic fields, experienced rapid advancement due to the availability of Bose-Einstein condensation. Furthermore, the ability to create and manipulate Bose-Einstein condensates has had a significant impact on the study of superfluidity. While superfluid helium involves strong interatomic interactions, Bose-Einstein condensates provide a cleaner system for studying the fundamental principles of superfluidity. Experiments with Bose-Einstein condensates have confirmed many theoretical predictions about superfluid behavior, such as the existence of quantized water. The creation of Bose-Einstein condensates moreover spurred the development of new theoretical frameworks for understanding the behavior of many body quantum systems. The Gross-Pityevsky equation, a nonlinear Schrödinger equation, has become a standard tool for describing the dynamics of Bose-Einstein condensates. This equation accounts for the mean field interactions between the atoms in the condensate and has been used to predict a wide range of phenomena, including the formation of solitons and the excitation of collective modes. The work of Cornell and Wieman also had a substantial impact on the field of quantum information science. Bose-Einstein condensates can be used as qubits, the fundamental building blocks of quantum computers. The ability to precisely control and manipulate individual atoms in a condensate opens up new possibilities for creating quantum gates and performing quantum computations. The reception of Cornell and Wieman's work was overwhelmingly positive. The scientific community recognized the significance of their achievement, awarding them the Nobel Prize in Physics in 2001. Jointly with Wolfgang Kettel, who independently achieved Bose-Einstein condensation in sodium, their work was hailed as a triumph of experimental physics, demonstrating the power of laser cooling and trapping techniques and providing a new platform for exploring the fundamental laws of quantum mechanics. A few initial critiques centered on the precise determination of the condensate fraction and the role of interactions between the atoms. Some researchers questioned whether the observed peak at zero velocity could be attributed solely to Bose-Einstein condensation or whether other effects, such as atomic interactions, might play a significant role. However, subsequent experiments and theoretical analyses confirmed that Bose-Einstein condensation was indeed the dominant phenomenon. Moreover, refinements in experimental techniques allowed for more precise measurements of the condensate fraction, further solidifying the evidence for Bose-Einstein condensation. Researchers also developed more sophisticated theoretical models that accurately accounted for the effects of atomic interactions, providing a more complete understanding of the behavior of Bose-Einstein condensates. The influence of earlier works on Cornell and Wieman's achievement is undeniable. The theoretical groundwork laid by Bose and Einstein on quantum statistics provided the conceptual underpinning. The experimental advances in laser cooling and trapping, pioneered by Chu, Phillips, and others, provided the technological tools. The expertise in precision measurements and atomic physics at the University of Colorado Boulder and the National Institute of Standards and Technology also played a crucial role. Conversely, the influence of Cornell and Wieman's work on subsequent research is equally profound. Their achievement inspired numerous experiments on Bose-Einstein condensation using different atomic species and in different trapping geometries. It led to the development of atom lasers and atom interferometers, expanding the field of atom optics. Additionally, it fueled theoretical advances in understanding many body quantum systems and opened new avenues for quantum information science. In summary, the 1995 paper by Eric Cornell and Carl Wieman detailing the creation of Bose-Einstein condensation in the gas of rubidium atoms stands as a landmark achievement in physics. It not only confirmed a long-standing theoretical prediction, but also opened up entirely new avenues of research in quantum mechanics and condensed matter physics. Their work has had a lasting impact on the scientific landscape, inspiring numerous experiments, theoretical advances, and technological innovations. The legacy of their discovery continues to shape our understanding of the quantum world and its potential applications. Their meticulous experimental design and insightful analysis serve as a testament to the power of scientific inquiry and the enduring quest to unravel the mysteries of the universe. The pursuit of extreme cold, once a mere curiosity, transformed into a gateway to a new realm of quantum phenomena, a journey initiated by a groundbreaking work.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.